Okay, good afternoon, everyone. I hope you are doing all right and ready to learn some physics. Okay, so today we're going to talk about applications of the Faraday's law we learned last class. So one application, very common application, is something like this. When we buy our device like computers, we may get something like this that we use to charge things. So what happens? There is one side that goes to the wall and another side goes to device. So that bulk has this transformer inside it. Okay. So usually this is how a typical transformer, looks like. And this is not the transformer we are talking about. Okay. So sometimes, part of the Denver metro, I see there are wires, they are underground, but in some part they are exposed. So you may see in some places there is this kind of device there. So it is also a transformer. Okay. So if you ever been to a place where this big poles coming, and then from there it starts distributing electricity in other places like a home. Okay, in those places you may see big such structure on the ground. Okay, so basically what it does is it's changing the voltage. So one example would be, for example, these days electric vehicles are getting popular. So when we use just 120-volt outlet, then what happens? Charging takes forever. But if we want to make 240-volt, then what do? We use this device transformer. Okay. So now it has coils, and then these cores we call iron core. Okay. And in this case, you see this is iron core, and these are the coils. And the coil that goes in the, let's say, input side, where the wire that goes to the wall, we may call that primary. And the one that goes to the device or your vehicle, that we call secondary. Okay. And now what happens is that this transformer do not work with DC voltage or current. It only works with the AC. And why is that? Because we learned that EMF is given by this equation, and this is induced EMF. And this EMF is induced only when the flux is changing. If flux is not changing, then they're not going to be induction. Induction is going to be zero. Okay. So how do we change flux? As we talked about, if we look at the definition of flux, it is product of area of the coil, B, magnetic field, and cosine theta. Okay. So now you can change angle. So maybe you can do something like that, and you change flux, or you can change the area of the coil. Okay. So in transformer, you cannot change the area of the coil anymore because it's for a transformer. Once you have a transformer, it has fixed coil. Okay. So that means the area of the coil is going to be fixed. And similarly, they are oriented such a way that you cannot change angle either. So that means only thing you can change is magnetic field. So now what happens is the coil in one side, when we pass the current, When current passes through this, it induces that magnetic field. So basically, it generates the magnetic field, I should say. So the current flowing through the coil acts like a magnet, right? But that current, sorry, the magnetic field in such coil, we also call solenoid, is given by this equation. So for a given coil, the number of density of the coil is fixed. This constant is fixed. So that means you can change magnetic field only by changing current. Okay. So if you are using direct current, that means the value changes only when it turns on and off. That's it. So that means, other than that brief moment, there's not going to be any induction. However, when we have alternating current, what happens? Alternating current, like if we were to plot alternating current, and this is how alternating current looks like, or if you like, you can also plot EMF and all, this current. They have basically similar sinusoidal form. So that means it starts from 0, goes to maximum value, and then comes to 0 again, decreases, so increases, decreases, and then reverses the direction and increases, and then decreases again and reverses direction, and so on. So it's changing all the time. Value is changing and direction is changing. So because of that, what happens is they're going to be changing flux. Now, this coil produces changing flux, and that flux, so this role of this iron core is to guide these flux. So rather than letting them escape, something like that, it guides them to the another coil. So that way, there is no loss of energy much, okay, with this iron core. So it basically directs the flux towards the another coil, so it prevents the leakage. But in that process, what happens is this iron core also gets hot. So that is a disadvantage. We'll talk about that later. But first, the advantage is that without that, this is not going to be very efficient. Okay, so that's what it does. Now, what happens? There is this flux, and flux is changing in this coil. Since it is changing, flux is coming and entering to this coil means the flux is changing here means it's going to induce the EMF and current on this side. So that's how transformer works. So now, the induced EMF in first, let's say primary coil, I'm writing one subscript for those. So there is this number of turns in the coil. So there are like thousands of coil, turns in a coil in big transformers. So now that is the EMF induced here. How about EMF induced here? So we can write that equation something like this. Same equation, but this is for the secondary coil. Now, whatever flux change is taking place here, that is being coupled or directed here. So that means rate of flux change, they are same. So that's why there is no subscript, new subscript in this rate of flux change. It is same for both coil. That's how they are coupled. That's how they are made. Okay. So because of that, what happens is now, if you were to divide one equation by another equation, then this is going to cancel. Or if you don't like that thing, then you can solve for this. And then whatever you get, you plug that in there, right? There are more than one way to do algebra. So when we do that, when we eliminate this, either this way or that way, we are left with this. So in this case, I divided this by this, and then this by this. So when we divide this by this one over here, what happens? This cancels, negative sign cancels. We have N2 on the top, the N1 on the bottom. So the ratio of the EMFs on the two sides, okay? Two sides means secondary and primary. So this is secondary side. So we may also write, sometimes you may see, we may write this with the subscript S. That means this is secondary. And similarly, we may write primary, P for the primary, okay? So this is the equation that allows us to figure out what's going to be the induced EMF in the secondary if we know what we are supplying and what is the turns, number of turns, or what's the ratio. So we don't even need to know individual turns. If we do, that's fine. We can just find the ratio. But if we are given ratio, then we can just plug in this. So for example, let's say the primary has, let's say, yes, my drawing has like 4 of them, right? So it looks like over here there is 3. So secondary is 3, primary is 4. So what is the EMF on the secondary side? This is 3/4 of EMF. See, the number of turns in this side is less. Because of that, the induced EMF on the secondary gonna be less than primary. See, this is only 3/4, right? 1/4 is missing there. Excuse me. My throat is a bit acting weird. So in this case, what happened? Let's say if we had 120 volt here, so that means if this was 120 volt, then this would be what? So 4 times 3 is 12. So 30 times 3 is 90 volt. So it goes, it brings down that 120 volt to 90 volts. So it's bringing voltage down. So we call this step down transformer. When you have number of turns in the secondary less than number of turns in the primary. Okay, so that's the kind of transformer is used, let's say, when we want to distribute from larger high voltage line to the our neighborhood. So we want a step down transformer in that case. But if we are generating power in a, that's where the generator we put, and we may be, let's say the generator, so we may be, let's say using water to generate the electricity, hydroelectric, or we may be using turbines, wind turbines, right? Or most commonly used these days are natural gas and coal. They use to, make steam out of water, and then they use that steam to spin the generator wheel. So in that source where the electricity is being generated, the voltage produced is not that high. But when we want to transfer to the place where it's being consumed in long distance, so we want to transfer a lot of power, and voltage low, so power is product of current and voltage. So if you have low voltage and if you are transferring large power, that means you have to transfer large current. And that any wire had some resistance, and especially when you are transmitting kilometers or miles, then the resistance becomes like not so negligible. Okay, so because of that, what happens is the power you generated that goes in heating this wire, and that is given by this I squared times R. So this is the loss, okay? Because it just dissipates energy in the environment after the wire becomes warm. It's just dissipating energy. So it's losing any power, right? We do not want to do that. So because of that, what we do is rather we use this transformer, and this time step up transformer. So that means it brings the voltage from low value to high value, very high values. So if you see tall transmission lines around the town, that means they have thousands of voltage. Okay. So they are high voltage, means current is small. So once current is small, the dissipated power in the wire becomes less. So that's why they are transmitting high voltage. Okay. So this is how transformer works. And we can have step up and step down transformer. Hopefully now you fully understand that. So now here is a question for you. So what do you think? 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see how did we do. So mostly C, it is step up transformer. High voltage, low current means low power dissipation. Okay. So now, so here you see this sign is for alternating voltage or current. So now what happens is we are saying ideal transformer. What it means is whatever power we are sending here, all the power gets transmitted to the secondary without loss. That's what we are assuming. But there is no such thing as an ideal transformer. There are always going to be some loss. This thing becomes warmer. So for example, if you are using your charging device in your computer, if you have used that for, let's say, 10 minutes, 15 minutes, and if you feel it, you'll feel the warmness there. Okay, that device becomes warm. So that means it's losing some energy. So that's why we call ideal transformer, means we are assuming that it's not losing. Okay, real, they always lose. Ideal means they don't lose. That's what we are assuming. Okay, so with that assumption, what we can do is we can say, okay, power in the secondary is same as power on the primary. So here I use this, subscript. You can see on the primary side, all the subscript are P, and on the secondary side, all of these are S, okay? So here there is core and this is flux shown by just one line, okay? So now we can use power equation. Product of current and voltage is power. So product of current and voltage in secondary is power at the secondary, and product for the primary is gonna be the power here. Okay, so current and voltage here for the primary, and let's say current and voltage is not shown here, but BP. Okay, another way to write it is by using Ohm's law. V is I times R, right? So we can replace this V by I times R. That way it becomes I times R means I square R. So that's what we are writing here. So depending on what we know and what we want, we can use one or the other. And of course, so this is we can use once we know, the transformer. And in this class, we're going to be just doing math on ideal transformer. So even if it does not say it's ideal transformer, you can still use this idea for this class, okay? And there is this equation we just wrote. We had written that in terms of EMF. Here, we are writing that in terms of potential difference, okay? So what's the difference between potential difference and EMF? The drop in potential in tiny internal resistance. So these sources, unlike battery, may not have internal resistance much. So that's why the EMF and voltage kind of equivalent, very close, okay? So that's why we can interchangeably use voltage and EMF. Okay, so now let's take a look at a problem, like what kind of problem we can expect or solve in a transformer. So in this case, it says step up ideal transformer has 32 turns in the primary. So primary means NP, number of turns in the primary is 32. It's a number, so it does not have unit. And in the secondary, it is 960. You see the secondary has 330 times more, looks like. If this transformer is producing or is to produce that much and that much current, what input current and voltage are needed? So that means we want that much over here in the secondary, means that's going to be the voltage at the secondary is 5200 volts, and then current at the secondary is 13 milliampere. So let's convert that to ampere. So milli has 1,000, or 1 ampere has 1,000 milliampere. So other way around, 1 milliampere has 1,000th ampere. So that means 10 to the power negative 13 ampere. So proper way to write this would be 1.3 times 10 to the power minus 4, but I'm just leaving like that. And what input current? So that means we want current in the primary. Okay, this, what is that? And voltage in the primary. So primary voltage is here. So there are two unknowns. Okay. So now let's see, looks like we can find a voltage just by using this equation. So voltage at primary divided by voltage at secondary. See, in our formula, we had secondary on the top and primary on the bottom. But you can easily invert this formula and write V1, V2, N1, N2. So why am I writing primary first on the top? Because we are looking for that. Okay, so we can use that, and these basically when this is primary, then this number of turns going to be on the primary as well on that side, and this is number of turns on the secondary. See how I wrote it? So here, see when there is two subscript on the top, there is two subscript on the top. And so that means whenever there is one subscript in the bottom, one subscript in the bottom. Similarly, when there is one subscript on the top here, then it has to be one subscript over there as well. Okay. So looks like BP, we can just solve by using this equation here, because all these are known, right? So NP in this case is 32, and then NS is 960, and then VS is 5200. So that 10 cancels. 30 times 3 is 90, so that this is 1/3. Now let's see if we can cancel with 3. 3 times 1 is 3. 3 times 4 is 12. So that means it is 140 volts. Okay. So now that is BP we found. Now we want to find IP. Okay. So next, IP. So primary current. How do we find it? So we can just say, okay, since this is ideal transformer or ideal transformer, power is same on both sides. So power at primary is equal to power at secondary. So that means power at primary. So we know voltage current, so we don't know resistance. And so that's why we want to just write this as a product of current in primary times voltage in primary is equal to same thing for the secondary. Okay. So now current in primary we are looking for, right? So that's what we are looking for, current in primary. So that means we solve for this, means the VP is going to go down and divide. So IS, VS over VP. So we have IS here and BS and VP. So VS we know is 5200 and VP is, we just found 140, and then IS is, it looks like we can just find the value in milliampere. I don't have room over there. So once we do that, we're going to get that in milliampere. If you want that in ampere, just multiply that by 10 to the power -3 or divide by 1000. Okay. So that's how we use that equation. So if the resistance was known, then I may be using either V square over R for the power, or I square secondary times R, this or that. Okay. So if the resistance here in the secondary is known. Okay, anything you like to ask or add on this one here? So what number did we get here? I think it was 30 here. So 30 times 3 is 390 milliampere. So what happens? Power is same, but when voltage changes, what happens? Current changes too. Here in the secondary, voltage increased, but current decreased. See here? Okay, maybe that is 173. I just try to do that in my head. Oh, there is 2. Okay, so 3 times 1 is 3, and there is 2. So yes, looks like it's going to be 7 there. And then there is that. So yes, you are right. The thing I did in my head, I made mistake. Okay, thank you for that. So that means this thing also changes. Okay. Again, thank you for doing the number in calculator. Okay, so now here is question for you. So that resistive load means that RS we had in this diagram, right? So the secondary, see, the secondary wire goes to the device, and device has resistance. And sometimes device resistance are also called load on the circuit. Okay. Okay, so it looks like we have a very nice problem here. It may take a little bit time. So let me open the poll. So a lot to read here. I'm giving you 2 minutes. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So here, let's see what we got. So secondary current doubles and the primary current doubles as well. Okay, Let's see. So in this case, the secondary winding is connected to a resistor load. If the resistance of the load is reduced by half, how will the current in the primary change and the secondary winding change? So secondary, so load is in the, secondary is connected to this resistor here. So resistor is secondary. So whatever current is in the secondary right now, when the resistance becomes half, remember what happens? For a given voltage, V is I times R. So when resistance becomes half for the same voltage, the current has to double. So current in the secondary doubles when resistance on the secondary becomes half. Okay, secondary doubles. How about primary then? Okay, so now power has to remain same on both sides. So looking at the current, what happens on the primary side? Voltage is fixed. It is connected to 200 volt. 40 volts means primary side voltage is not going to change. What has to change? If it does, then secondary going to change. So anyway, so that is equal to IS BS. Okay. So over here, what happened? Current double. So that means voltage became half. Hold on. So current doubled. So that means voltage actually doubles over there. But what happens here? So power remains same. So here the power has to remain same, right? So in this case, what happened is like we, by making current half, the voltage basically doubled. But we cannot say voltage doubles. If we look at something like that, voltage is not going to double because voltage simply depends on the ratio of the turn and the primary voltage, right? So secondary voltage is fixed. So that's why when we change the current, what happens here? Resistance, when we change the resistance, the current increased. But since the power remains same, though, so because of that, the current on the primary also has to double. So suddenly it's going to start drawing more current because voltage cannot change. So yes, B seems correct in this case. Oh, looks like I have to exit from here. Okay, so now there is another question. So in this case, there is this, looks like a battery connected in this side on the primary side of this transformer, okay, which has voltage V. So battery is connected. 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So mostly we are getting C. Okay, so this is battery. That means current is constant. What that means? Flux is not changing. So that means induced EMF gonna be 0. Okay, so we need AC source, but this is a battery. It is not alternating. It's not changing. Okay, so because of that, what happens is there not going to be any induced voltage here in this case. So this question is to remind you that transformer only uses the alternating current source, not battery. Okay? It says in a steady state, means it's not changing. When current is not changing, flux is not changing, means the voltage is not changing. So if it was, then this would have been correct answer, but since the source is battery, in this case, D is correct answer. Okay. Anything you like to add or ask here? Okay, so now I said in a transformer, what happens in the core where the iron is, there is always, some power loss over there. It gets warmer, hot. That means we are losing energy. That electricity gets converted into heat energy. So how does that happen? That is called eddy currents. So what is eddy current? So if we have a, flat metals, so for example, the cores are like flat metals like this, let's say, right? Or could be bigger like this, but this is not metal. I'm just trying to show you the shape, okay? So when you have something like that, and for example, let's say if flux is changing there, so flux can change several different ways. We talked about it, right? So in this case, what I'm saying is, okay, let's suppose there is a magnetic field and we are pulling a metal, something like this, in between the magnetic field. So there is a magnetic field and there is just a metal, okay? What kind of metal? Like iron, ferromagnetic material. So, if we pull that, what happens? Since there is, so since it's moving, now there are going to be change in magnetic field. So part of this, see, the one that is in this side, so here, V is this, means this thing is moving to the right. We are pulling this to the right, okay? So that means it entered from the left and then went out, let's say. So it's a moving conductor in a magnetic field. That's what we are saying here. So, talking about that. So what happens at the beginning when it is not in the magnetic field, flux is 0. Okay. When it is outside the magnetic field. Now, when it enters, now then what happens? Flux goes from non-zero to 0. Sorry, no, 0 to non-zero. Okay. So flux 0 here, flux not 0 there. Okay. So that means flux changed. Flux changed means whenever flux changes, what happens? So see, this is a metal plate, but we can think of it is made up of, a lot of coils, for example. There is, the current can circulate here because there is no broken path. So current can start circulating there. So what happens is this changing flux induces current here. And if we were to use that Lenz's law, we can tell which way the current going to be circulating. So in this case, original magnetic field is in that direction, is step 1. And then since it is going that way, means flux is increasing, I is increasing. So to oppose that, it has to be developing field in the opposite direction. So that's why the induced is given by this blue color. Original fields are drawn by green colors here, and the induced is drawn by blue color here on this side. Okay. So that means if induced field is up, if you were to point your thumb up and crawl your finger, what happens? Your finger crawls that way. So that way we know this is circulating that way. So now this current circulating here. Okay. So this current circulating means the electrons are moving there. So they feel resistance in the, there may not be very large resistance, but any metal has some resistance. Okay. So it experiences that resistance means that current, the current develops that eventually dies down because of the resistance. So when it dies down, that means that energy gets converted into heat. Okay. So this eddy current, and the eddy current generates heat. So eddy currents are circulating this way here, but when the plate is coming out from the magnetic field, it now circulates in opposite direction. Can you tell why? Why here? So we talked about, how to get direction of current in this side. Can you tell why the current is circulating kind of opposite on this side where it is leaving the field? And I'm claiming that induced one has to be this way for this current to go that way. So why the induced is in the same direction now as the original? Over here it was increasing. So to oppose the increase, it has to line up. The induced field had to be lined up in the original direction. So over here, when it's leaving over there, what happens? It's going from high magnetic field or flux region to 0 flux region. So that means now flux is decreasing. So to oppose that, it has to generate the induced EM, field in the same direction. And to generate this field in that direction, the current has to circulate other way around, because now thumb, instead of pointing up, thumb is pointing down, means now fingers are curling in the opposite direction. Okay. So now these eddy currents, they, like as long as the field is there and there is that, flux is changing, eddy current gonna keep on developing and keeps dying, and that means it keeps generating heat. Okay, as long as it is operational. Okay, so the eddy currents are bad for the transformer. We don't want to lose, right? We want ideal transformer. So that's bad for transformer. And that's how it looks like. So if you were to make a solid core, that means just a slab, then it's gonna kind of generate this runaway current or very large current, and they're gonna be even more loss. So to prevent from that happening, what they do is they laminate, means they put these segments, different segments. So that's why if you look at some transformers, sometimes you may see these cores are laminated so that it does not you know generate that eddy currents combine and then forms to like runaway kind of current. So to prevent that from happening, high eddy current, they do the lamination here. So heating on a transformer is bad, but just like friction is bad, right? But friction is also good. Without friction, we cannot walk, right? We cannot drive. So similarly, with this knowledge, how it's generating heat, uh, or there is opposing force there gonna be. Based on that, what we can do is basically make use of that. So for example, here there is this braking. So in this case, there is this electromagnet. And then there is this, let's say, so this thing spins and that spins the wheel, means this is spinning, okay? So if you want to stop wheel spin, then you want to put brake on this, looks like rusty iron wheel there, right? So you want to slow that down. So just like we saw here, this metal thing is moving in a magnetic field. What they do is they have this electromagnet. So whenever they need to brake, you just turn on the current in the electromagnet. So that means now suddenly there is magnetic field, okay? And then it's moving in a magnetic field just like it is, okay? So what happens? It opposes the change. So that means it produces opposing force, and that force acts like a braking, okay? So that is good use. Another good use is induction stove, right? So it uses that coil, and then rather than heating the filament here, so the coil stove, they have coil there, so it hits the coil, and then it gets transmitted to this, okay? So in that case, a lot of heat get out from there, so that means there is loss of energy or heat. When we are using our conventional type of stove top that has coil in it. Yes, in some the coils are easily visible. In some the coil may be hiding, so you may see the plane, but it is still hits from the bottom, so whole surface gets hot, okay? And some heat is basically going in the environment, in the air, okay? But if we use this, then what happens is it basically generates the eddies over there on the pot. So that's why you have to have a particular kind of pot that generates the eddy. So it has to be ferromagnetic. So for example, this stove, induction stove, you can use your, those cast iron pan just fine. But if you have copper, you cannot use it because copper is not ferromagnetic. So even you may see the, pot with the copper on the top, on the bottom, they have this ferromagnetic material clad at the bottom, on those kind of pot. So that's why you need a special kind of pot. So most of these days, all the pots basically comes with that kind of thingy, but some pot may not work. So how do you figure out whether it's going to work or not? So if you have a magnet, if it sticks, if the magnet sticks in your pot, then it's going to work in induction stove. Okay. Okay. So that's the use of eddy current. So now we talked about why the current was circulating this way or that way over there, right? So we talked about that. And let's see if you got that. So here is a question for you. So this time it's moving that way. There is a magnetic field. So this magnetic field of the cross means, oh, I forgot. Is it going in or coming out, folks? In or out? Can you type that on the chat? Okay, so cross means in. Okay, thank you for reminding me. So, okay, so cross means going in. And now this thing is moving in that kind of field. Okay, how do the eddy currents circulate on the left and right side respectively? So left side means this side, okay, where it is leaving, right? So here left side leaving, left, leaving. Right side, it is entering, right? So it is entering. Okay, with that, now I'll let you work on this and I will give you 2 minutes. So make use of your hand and time. Okay, figure out. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what happens here. So B and C. So both of them opposite each other. So now which side is clockwise versus which side is counterclockwise. So it's a leaving here. So means flux decreasing to oppose it induces in same direction So in this case, B induced also has to be going in to the phase. Okay. So if I put my finger, thumb in the direction into the phase, my fingers crawling this way, is that clockwise or counterclockwise? So let's see which side it's asking here. How do the eddy currents circulate on the left and the right side? So left side is this. So it looks like it's going to be circulating clockwise. So see, it's decreasing. To oppose the decrease, it has to increase, means it has to line up itself in the same direction as the original. So to get the field down, your thumb has to go down. My screen is flat on the table. Okay, so that's that. So that means it is going clockwise. Can you verify that by doing it? Okay. On the other side, it's going to be exactly opposite. So here it's entering, means increasing. Increasing flux means to oppose B induced gonna be coming out. So coming out. So that means now my thumb has to be pointing up, means the finger has to crawl that way, which is counterclockwise. So it looks like B is correct answer. So did you folks chose B or C? B and C, but there are more C than B. Is left and right reversed? When I see versus you see, I hope not, right? This is left side for me on the screen. I'm guessing that is left side for you as well. Let me know if it is other way. Oh, looks like it's time for a break. So let's take break. Okay, folks, so welcome back. So when we are talking about electric potential, electric field, we talked about a device called capacitor. And another thing, resistance, we have, we've been talking about it. So now with this coil, we can make another device. And that's called solenoid, right? And also called inductors. So when we pass current through it, what happens? It behaves slightly different than simply if it was just a wire, not coil. Same wire, right? If it is straight and you pass current, it behaves differently than when you make coil out of it. So why does it do it? Basically, it's a inductance, okay? So over here, let's suppose we have a coil and we pass a current, okay? So something like this, a coil, and we pass a current, and that portion, just one is over here first. We are passing current on that one. Now, in this case, we have another coil as well, just like we had for the transformer, right? So transformer, by the way, symbol of the transformer is drawn something like this. Two lines in between, and then coil here, okay? So symbol of transformer. So this means iron core, and this is primary coil, and this is secondary coil. So we have here two coils, like a primary and secondary, but they are not in, there is no iron core in this case. So when there is iron core, what happens? Basically, in case of transformer, we have coil here and we have coil here. We are putting them side by side, but even if they are not side by side, if the one of the coil was somewhere here, the sum of the field is still going to pass through that, but not as much. Okay, so we want to keep this closer. So when we pass changing current, there are going to be induced EMF here, right? And then the induced EMF from here, so that means gonna induce EMF over there. So that is like a mutual thing, okay? So this is called mutual. And in mutual, there are two coils involved. But we can have just one coil, and it turns out, even if even when we are passing current, changing current, it has to be, my bad, I did the battery here, so should be changing, okay, changing voltage. So even if we have just one coil, what happens in this case is that once current flows, they're going to be changing flux, okay? Or if there is just a battery like I have connected here, they're going to be momentary change in flux, right? So for example, at the beginning, when this circuit is open, there is no current, so flux is 0. Now, when current is flowing, there is flux. So it went from 0 to high value. So during that, change for that fraction of second, there is sudden increase of flux here. So to oppose that increase, so even when there is this battery, not AC source, even if there is just a battery, what happens for that fraction of a second? There going to be surge of flux there, surge of flux from 0 to maximum value for that fraction of second. After that, this maximum value remains there as long as current is flowing. So after this becomes a maximum, nothing changes. That's not interesting, and we are not interested on that. What we are interested is during that, when you turn switch on, current goes from 0 to maximum, means flux goes from 0 to maximum as well. So there is changing flux. So that changing flux, basically, now to oppose that change here, this is a coil, so that's gonna basically now induce current or EMF such a way that the flux is gonna be, the new flux, induced flux is gonna be opposing it. And that's what this green lines are. Those are the induced flux, okay? Those are induced, these are original. So why they are, pointing opposite direction? Because when we turn on switch, what happened? It went from 0 to maximum, so it increased, okay? So that means, so flux in this direction means that is equivalent of saying, okay, there is now, since it is opposing this, the flux due to this orientation, so that means the other one must be pointing in opposite direction, okay? When current is increasing, it's going to generate in that direction. So at the beginning, what happens? There is maximum current, but before the current get maximum, same time what happens? There is that maximum EMF in the opposite direction. So because of that, it doesn't allow this current to suddenly increase. So there is no sudden surge in current in the circuit. So it has to go slower. Okay. So it slows down the process of increase of current in the circuit. So it smooths out the change in current in the circuit. So that's the use of this. So this phenomenon is called self-inductance because it's happening to the same coil. And see, is this flux phi, let's say, through one coil, one turn. If there are n number of turns, total flux is going to be that, okay? And that flux is proportional to the current. Larger the current, larger the flux. We know that. So this L here is a constant, like a capacitance for a capacitor. We have this constant, we call that inductance of an inductor. So inductor is a device, name of the coil is inductor, okay? And its property is the inductance, and that is given by this constant, okay? So total flux is proportional to the current. So, but it also depends on the property of this coil. So that's why it is called inductance. Just like we had a capacitor, Q is proportional to change in voltage, and that proportionality sign we replaced by C, and we said that was capacitance. Okay. Over here, we are writing in terms of flux and current. Okay. So if I were to solve this, so here, when I do solve for C, it becomes Q times delta V, right? Similarly, I can solve this one for L. Okay. So it becomes that. So here, this is number of turns in a coil. So this is the inductance. Okay. And we learned that this capacitance basically depends on the size and shape of the plates that we use to make the capacitor. Just like a garbage can, the size of the garbage can does not depend on how much garbage or the charge we put in. Similarly, this inductance, although it may feel like, okay, it depends on that. But remember, this just like Q and V proportional means by whatever amount we increase the Q, delta V increases by same amount. Same thing goes here. By whatever amount we increase the flux, the current increases by same amount. And in this case, this would be induced current. Okay. So by changing flux, by increasing flux, we are increasing current. By decreasing flux, we are decreasing by same proportion, means this L remains constant. So L, uppercase L, is the symbol for inductance. So now, what is the unit? So to find the unit, we need to make use of unit of these quantities. N being number, it does not have unit. And we learned that the flux has a unit Weber, but that Weber and the unit of current ampere, we can, let's say, rearrange that one little bit. So here what I'm doing is dividing by second and multiplying by second, because Weber per second is voltage. How do I know that? Because EMF is negative n times delta phi over delta t, right? So this EMF has a unit voltage, N and negative sign, they don't have a unit, and flux has a unit Weber. So Weber per second is voltage. So that's why to get voltage out of that, I'm writing something like this. Okay. So now it becomes voltage times second divided by unit of current, which is ampere, and that is called Henry. Unit of capacitance was farad from Faraday, right? Over here from our dear Henry. Okay, so now looks like a bit long question here. Okay, 30 more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. So we are getting a bit more D and some A and C. So I was reading through them and looks like D is correct answer because I know A is not correct. It says mutual inductance depends only on the number of turns in the coil B and resistance of A. So in our previous equation, we did not have any resistance. Resistance gonna affect current, but there is no direct relationship between that. We know that. And it depends on number of turn, but not just, like depends only on, it says. So yeah, it was kind of close for the number, but other things kind of, not totally correct. Musical inductance is solely determined by the resistance. So just like I said, it does not. So there is no mutual inductance between the coils if coil B is not physically connected to A. And we saw it happens because it gets connected through the flux. So for flux, we don't need connection. Okay. And so all of these are incorrect, means this must be correct. The mutual inductance is influenced by relative orientation of the coils and the, yeah, so if we bring like let's say if we tilt, then all the flux not gonna get into the coil, so that makes sense, right? And the permeability of the medium, right? So if we, like let's say if we have a one coil and then there is iron and then there is another one, so that means the medium has now some permeability, so that helps. So yes, so that one. So if we can rule out, we can say this is correct, and otherwise, of course, the inductance, the mutual inductance means flux has to be coupled effectively. So more effectively it gets coupled. So just like in the iron core on the transformer helped, just like that over here, if we have some medium that helps, that's great. And then if we put them, directly opposite, or let's say the area of the coil becomes parallel to this, then flux is going to be maximum, right? And so that's why D is the best choice here, which I already said. So now, so we can put an inductor in a circuit just like we would a resistor. See the difference here? Inductor is a coil, so symbol gonna be like that. Resistance, just like we had a capacitor on the circuit, right? So we can put that. So let's suppose we have some EMF there, and current I flows through that. So in that case, we know the voltage over here in the resistance is R times R, assuming it has a resistance R. And if capacitance is C over here, then how much voltage they are going to be? So we can write that by using this Q is equal to C times delta V equation, right? So we know capacitance. So delta V is going to be Q over C, and maybe we want to write this in terms of current, and Q is, let's see, I times T. So yes, it is not a straightforward equation, but you can write potential difference across the capacitor. Similarly, we want to write potential difference across the inductor. Okay, so how do we do that? So potential or EMF based on, so the EMF here is the self-induced EMF we already talked about. By the way, this EMF is also called back EMF. See, it is generating in the opposite direction than the source that is supplying the current. So that's why it has this name back EMF as well. So that is given by this based on Faraday's law, we know. And then from the self-inductance, we learned that if we have N times pi, we have L times I, right? So we want to replace this N and pi, but we have delta. So N times delta pi, so pi is changing, N is not changing. So that's why the change I'm writing in terms of delta pi. So when it's changing over here, it's going to change over there as well. L is a constant, it does not change. So that means it's going to be current that's going to be changing. So that's why I'm replacing N times delta phi by L times delta I, and that is the EMF. And this negative sign simply tells us that it is induced in opposite direction of the source EMF. Okay, so that is basically coming from Lenz's law. We know that, right? So that is the amount of EMF that's going to drop. So just like we can write I times R here, we can write L times delta I or delta T. So if you, I don't expect, but if you have used calculus, then this thing is also written something like that. And with this and that in a circuit, it becomes differential equation, and we can solve that, and it gives the exponential solution. So we don't do that here, only in general physics, because we don't use calculus here. So what we can do is we can say, okay, it's that, and we can say, okay, uh, later we can look at, like how the current is changing. But at this point, okay, let's say if this thing is in a circuit, how much potential drop is there? This much, okay? So that we can tell. And just like when we have a capacitor in a circuit, capacitor, same length, right? When we have a capacitor in a circuit, we learned that energy stored in capacitor was half C times V square or delta V square, okay? Similarly, energy stored And this turns out to be inductance times current squared. Looks very similar. Okay, so that's the energy. And where is that energy coming from? Because of the magnetic flux. Okay, and our device may look something like that. It has certain number of turns and it has a length L. Okay, so this kind of device is also known as solenoid. If it is in circuit, we may say inductor. Okay, if we are using this as some other devices, for example, let's say MRI machines, they provide magnetic field uh, by passing current in this kind of coil. Okay, so in that case, this coil acts like an electromagnet, and we can say, okay, it is a big solenoid. Okay, so inductance of a solenoid, just like we saw in the previous slide, we had L is N pi over I. Okay, so over here, pi is flux and flux is cosine theta. So when we use this as a solenoid, we always orient magnetic field in A such that cosine theta is always 1. We want to get maximum. So that's why we can write this. Okay, so here the A is area of this coil here, and B is, of course, the magnetic field strength. Okay, now we learned that if we have something like this, the magnetic field is given by this equation. So we learned this in the chapter of magnetism. This N over L, we wrote that as a lowercase n. Okay, so that's that. So now with that, I can write something like this. So what this tells us is that, see, the current now cancels, giving us this. Just like capacitance of a capacitor was dependent on just this factor, area of the plate and separation distance between plate and the permittivity, there is this. So the inductance depends simply on the number of turns, area, and the length. So that means just the property of this coil. If we know the coil, we can just do counting and some length measurement and find the L. We don't have to know current, we don't have to pass current or anything like that. Okay, so it is also like a garbage can. The size, how much current flowing does not, you know, make difference in terms of what the inductance of a solenoid is. It purely based on its geometry. Okay, and the previous question was kind of something like that as well. Okay. Okay, so what did we learn here? Inductance of a solenoid can be written by this equation, just like we did capacitance of a capacitor like this. Okay, and then energy like that, and then induced EMF when it is in the circuit and when current is changing. That's that. And by the way, once current stops changing, change becomes zero, means this whole thing becomes zero when current is not changing. So that means once the current becomes maximum and not changing anymore, let's say if you connect to a battery like this, then it acts like a wire now. Okay, simple connecting wire. So it plays role only when you are turning on current and turning off current. For most part, what happens? It acts like just a wire, regular wire. Okay, so that is kind of nice thing about it. So now I have a question for you. 30 more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. So mostly B. So it is n squared. So 1 and 4 kind of makes sense, but is it B or D then? So now which one has the double? First has the double, means it's going to have 4 times. So 1 over 4. So yes, B is correct answer here. If the second had twice, then D would have been correct answer. Okay. So now let's look at problem related to inductor in a circuit here. So there is that much Henry solenoid, and the current increases from that much to that much in that many seconds. Find the average EMF in the solenoid during that period. Okay. So basically it is a kind of plug-in chug formula. So we are given the inductance. So this is that. So L in this case is 0.080 Henry. And current, it is given in milliampere. So maybe final current, initial current is 20 milliampere, 20.0. So it looks like this is too sig problem. 0 milliampere. So that becomes 20 times 10 to the power negative 3 milli, not milli anymore, it's ampere. Initial current and final current is 160 milliampere, and we can convert that to, and that happened during this time interval. Okay. So here change comes from this final minus initial. Time interval is there, so everything is there. So negative simply means it's back EMF, or it opposes the original. Here I did not change, but if we were to change, we can write 10 to the power negative 3 outside here, and that's going to be ampere. Okay, and we can do the math, and looks like that's going to be the value. Hopefully I calculated that correctly. I usually use calculator, so should be fine, but sometimes I try to be smart by just do that in my head and messing up. Okay, now let's look at an example where there is resistance in the inductor. So since there is inductor, what happens? There are going to be EMF. So there is in the circuit, there is source of EMF, which I'm saying, okay, that's a battery EMF, okay? And then this is the back EMF or induced EMF, okay? So I'm using L subscript to denote that it is the induced, self-induced EMF in this inductor, okay? So how do we analyze this circuit then? So in this case, the EMF over there, that is, see, it is backward, but its value is that much. Okay. And over here, if current I is flowing, then it's going to be I times R. So now what happens is, basically, if I were to write the equation, EB, so if current is going something like this, then what's going to happen is that and this is flowing in same direction, so decreasing, so that's going to be I times R. Over here we say, okay, it increases in that direction, so I'm using Kirchhoff's rule, right? So in that case it becomes negative to positive. It goes from low to high, so final minus initial is positive, so it's going to be that, and that's going to be 0. So we can write the equation. But when we do that, what happens is there is this thing there, and then plus that L delta I over delta T. So this equation is not algebraic equation. This is actually differential equation. So to solving that requires the knowledge of calculus. So I am just writing the solution here. If we were to solve this equation for current, it turns out to be something like this, just like we had for the capacitor. We had the similar equation for the capacitor. So in this case, we have 1 minus this exponent there. So what that means is when this is 0, this fraction is 0, what happens? When this is 0, then it becomes E minus 1. So we can write that as a 1 over E. So when does that happen? When time is very small, and then this ratio can be 0. And we can have something like this. But when time is very large, then what happens? This thing is like E to the power infinity, means or very large number here, 1 divided by very large number is 0. Okay. So at the beginning, what happens is it is trying to get, like let's say it says, okay, there is this maximum current. And when this is 0, sorry, when this whole thing is 0, then it's going to be 1, and that is going to be current going to be 0. So the current is changing as an exponential. So in this case, what is the maximum value of current? So just like I said, after a long time, current becomes maximum. When that happens, this acts like just a wire. Okay. So in that particular situation, when time is long, after a long time, and that takes less than a second, long time takes less than a second. Okay. What happens is now it acts like just a wire, connecting wire. So current at that moment going to be just this voltage here on the battery divided by R given by the Ohm's law. Okay, so that's what I'm writing. Okay, and this is characteristic time, and that depends on the inductance of the inductor and resistance of this resistor in this circuit. So we had this characteristic time for the capacitor circuit as well. So same idea here. And if I were to plot the current, what happens is at the beginning, because of that, generation of this, it kind of cancel that change. And because of that, the current cannot start with a maximum value. Rather, it starts from 0 and then slowly increases. And after a long time t, it becomes large. okay? And when time is equal to tau, that's when it becomes 1, okay? So in that case, this number becomes just like I had written 1 over E, okay? When t is tau, that's when that becomes, okay? So in that case, this is that. And by the way, this IF is like a final. You can read that I max, okay? I did not have much time to, make plot myself, so I copied the plot, but the notation is slightly different, okay? So that's my max. So this is like 63% of the max value. So when that, so what is the value of current? So current is increasing and it is 63% of the maximum value at first time constant, tau, and so on. So that's what it is saying, okay? And I have this question, but I'm just noticing I also have this one here. So what we were just talking about is used here. So let me quickly, since, oh, it's already 50, huh? So in this case, it says find the characteristic time. So that means you use this formula. So L and R are there, right? So you can do that. What is the current in the circuit after one characteristic time? Remember, it's the 63% of maximum, or you can calculate that since you know characteristic time. But looks like to find that, what is the current long time after? So you need to find Imax. Imax is this. Once you have that, you can plug that in there and T tau, or it's just 63% of that. Okay, so that's how you solve this problem. So I give you hint and think of this as a homework, folks. We don't have time. So I'm stopping here. Let me know if you have question.